Okay, this is the second half of lesson 9.2. So we're talking about two-sided tests. Whenever you have an alternate hypothesis where it's not equal to, that's a two-sided test. So that means that we're just trying to say the null is not true. So it could, maybe the true proportion is bigger or smaller than the null. So it could go in either direction. This especially affects you if you're doing this by hand. If you're doing the norm CDF, it's going to have an effect. We'll show you what that means. It's not going to, if you use the calculator to calculate the number, it's going to catch your mistake here. There's oftentimes a mistake that students only do one-sided when it should be two-sided. Okay, so this might be an example of a two-sided test. According to the Centers for Disease Control, 68% of high school students have never smoked a cigarette. This person wonders whether this national result holds true in her large urban high school. For APSTAT's class project, she surveys a random sample of 150 students from her school. She gets responses from 150 students, and 90 say they have never smoked a cigarette. Is there convincing evidence that CDC's claim does not hold true at her school? So first of all, let's just kind of look at this. So 90 divided by 150 is 0.6. So 0.6, which is not all true. So that's less than 68%. So it's not exactly equal. So really, on either side, you have room to say, well, let's investigate further, right? Because we're not really going to either side necessarily. It could have been more, and you go, okay, let's investigate further, because we're trying to prove this not equal to, because the alternate in this case is going to be not equal to, because it says, does it not hold true? It didn't say, oh, less than that or more than that. It didn't give you a direction. So really on your alternate, you're just going to say P not equal to 0.68. And so either direction will give you, could give you enough proof to say, hey, this is not accurate. And the alpha level here is 5%. You would name the test. It's still called a one sample z-test for proportion, or one prop z-test. Simple random sample, I think it said. It actually said the words surveys a simple random sample. Less than 10%. We think that 150 students is less than 10% at a large urban high school. And large counts, again, we're doing n times p, not p hat. So n times 0.68, which is 102, which is greater than 10, and n times 1 minus 0.68, which is 0.32, which is 48, which is also bigger than 10. You plug in the numbers. So p hat is 0.6. We did that. And then you plug into the formula. So it's p hat minus p over square root of pq over n. And we get a z value of negative 2.10. So now you can get your calculator out if you want. And this is where the mistakes come in, actually. So this is all pretty similar to what we've done before. So if you are graphing this or doing norm CDF, you go, okay, negative 2.10. So you go menu 652, and you go negative infinity to negative 2.1. And we can just leave, because that's a z value, we can just leave it as 0, 1. And a lot of students will put that as their answer. I contend that multiplying that by 2 would be the correct answer. So let's do it the other way and see if the calculator would have caught that error. So if you go menu 6, 7, and then one prop z-test is number 5. The null is 0.68. We took a sample and got 90 out of 150. And we think it's not equal to. So the default is not equal to there, and we're going to keep it there. And I think it's going to match my p-value of 0.035. You can see that if you look back, that's what I got when I multiplied by 2. And if we only did norm CDF, we only get half of that value. So why is that? So if you draw the normal curve, in the middle is the 0.68. And this was, let's see, the z value was negative 1.1. So somewhere in here is the z-value. So you're shading this way, and you might just go, well, how come you don't just figure out that area? How come we had to multiply by 2? Because it's a two-sided test, you're also finding the z-value over here and shading this way. And so that area to the right is the same as the area to the left. That's why in my calculator, I multiplied the norm CDF by 2. So that's the hard part to remember. If you do it by hand, it's very possible that you'll, kind of plug it in, get that number, go, oh, okay, that's my answer, but you have to multiply it by 2 because it's a two-sided test. So that's the difference with today's lesson than what we had previously. And so you do that in your calculator, and then you see at the end here, if you look closely, it says times 2 or multiply by 2. So you take that number and multiply by 2 to get the 0.0357. Because our p-value of 3.5% is less than our alpha level of 5%, we reject the null. We have convincing evidence the proportion of all students at her school say that they have never smoked a cigarette differs from CDC's claim of 0.68. So we're not saying the direction. We're not saying less. We're just saying we think it's different, right? That's what the wording was, and that's what we say. We don't think the claim that CDC is making is true based on the data. Boy, this is a detail that only a St. Mary's student would fully appreciate here. So y'all are so good at English, and so just the way you say this, you have to be careful. If you say it wrong, like if you said that we have convincing evidence, the proportion of students at our school who said they have never smoked differs from the CDC claim. That's not proper. The portion who said that is who said it is actually the sample proportion. You should say it, the proportion of students who would say they have never smoked. That's a proper way to describe the population there. So, wow, the wording of that is very, very close, but I think you might understand that maybe even better than I do here. So now there's a link between confidence intervals and two-sided tests. So yeah, they kind of look alike, right? That's what a confidence interval kind of looks like. So a 95% confidence interval gives an approximate set of nulls that should be rejected by two-sided tests at the 5% significance level. So there's actually some connection there. You get similar results really between the two when you do those. So oftentimes you perform a significance test to find convincing evidence for the alternate, right? So you're trying to prove the alternate true. But they would make a type 2 error if they failed to find convincing evidence for the alternate. How likely is it to avoid a type 2 error? So the opposite of a type 2 error is the power of the test, the inverse, the complement, however you want to think about it, but they're definitely related, but in one's going up, the other one's going down in the same exact proportion. So the power of test, the ability of that test will find convincing evidence that for the alternate when a specific alternative value of the parameter is true. So the power is when you reject correctly. So you reject the null and you're accepting the alternate. You are actually accepting the alternate in this case. We never accept the null, but we can accept the alternate. When you reject the null, you accept the alternate. So we're saying the alternate is true. You're finding evidence for the alternate. That's what power is. Let's go back to the battery example. Again, the null is nothing's unusual. They get 30 hours. The alternate is we think it's more. The new batteries are more expensive. So the company would like to be convinced they really do last longer. The power of the test to detect the null, detect that mu is 31 out, is 0.762. Interpret this value. So the power of the test is when you correctly reject the null, right? So the probability that the alternate is true is 0.762. So if the true mean lifetime of the battery is 31 hours, so do you see we're saying the alternate is true there? So the null is 30 hours. If we rejected the null, we're saying the alternate is true. So If the alternate is true, the true mean is 31 hours. There is a 76.2% probability the company will find convincing evidence for the alternate. So if the true mean is the alternate, there's a 76.2% chance that the company will find convincing evidence for the alternate, that the mean is greater than 30. So in the previous example, the probability of rejecting the null when the mean is 31 is 76.2%, because again, power is rejecting the null correctly. So what's the probability to make a type 2? So if you know power, the nice thing is you kind of know type 2. There's a relationship there. You just do 1 minus power would be type 2. Because if you either reject the null or you fail to reject the null when the mean is 31. Those are the two options. So they're going to add up to 100%. This is the formula. It's very nice to know this. Power is 1 minus the probability of type 2 error, or type 2 is 1 minus the power. So they're definitely like complements, inverses of each other. One goes up, the other one goes down by the same exact amount. What can researchers do to decrease the probability of making a type 2 error and increase the power of a test? So these are things you can do to decrease the probability of making a type 2. That can be nice, but it increases the power, right? So make the sample size larger. That is going to decrease the probability of type 2. The significance level, alpha, is larger because, remember, alpha and beta are related. If alpha is bigger, beta, which is type 2, alpha is type 1, type 2 is going to get smaller. If type 2 gets smaller, the power gets larger. So alpha and power kind of move at least somewhat in tandem. Not exactly the same way that opposite, but somewhat in tandem. At least one goes up, the other one goes up. And finally, the null and alternative parameter values are further apart. We can't do anything about that last one, but if we get results where the null and the alternative are way far apart, which happens sometimes, that does increase the power. So it's kind of like your results are so extreme that the power goes up, because you got really extreme results. This is just a way of viewing the relationship of type 1, type 2, and power. So if you see at the top, suppose the null hypothesis is true. Probability of type 1 error there is in red, right? So that's a type 1 error. That's called alpha. Alpha, and even has a little symbol there, alpha there. Type 2 error is called beta. And you can see that that's, by the way, suppose the null hypothesis is not true, but you have failed to reject, right? So you made the wrong decision there for type 2. That's the beta. And the power is the complement. You can see that those two add up to 100% there on the second normal curve there. So if I move this, you can see how they related. So type 1 got bigger, type 2 got smaller, power got bigger. And power got bigger in a relational way. Like if type 2 was 5% there, power would be 95%. If this goes the other way and type 1 gets smaller, type 2 is going to get bigger, which means the power of the test is going to get quite a bit smaller, right? So in the power in type 2 add up to 100% there. You can see that. So let's just watch that again. Type 1 increases, type 2 decreases, and power and type 2 are related. They add up to 100%. So there's very much a connection there. I really like this visual for you seeing the relationship of how all three of those things work in tandem. If you can kind of remember that, that's really good. The researchers at an Alzheimer's project want to test the drug manufacturer's claim that fewer than 10% of patients take the new drug will experience nausea. Okay, evidently that's a problem with some of the drugs. So they want to carry a test. The null is 10%, experience nausea. The alternate is we think less than 10% should. So earlier we mentioned that the power of the test to detect this is 0.08. Check p equals 0.8. Uses a random sample of 300 patients. The significant level of alpha is 0.05, is 0.29. So the power is 0.29. Determine whether each of the following changes would increase or decrease the power of the test. Explain your answer. So wow, this would be good if you could get all three of these right. So the alpha is 0.001 instead of 0.05. So I made the alpha level smaller. What's going to happen to power? So alpha is type 1. So type 1 got smaller, which means type 2 got bigger, which means power should get smaller. Decreasing makes it harder to reject the null when the alternate is true. If the true proportion is 0.06 instead of p equals 0.08. Okay, so that's not as obvious. So it's increased because it's easier to detect a bigger difference between the null and alternate parameter. So if you look at the back at the question, so 0.06 and 0.08, where the null is 0.10. 0.06 is more extreme, right? That's a bigger difference between the null and the sample there, right? So if the true proportion was 0.06. So if you get a sample result of 0.06, you go, oh, there's some power there because there's a big difference between 0.6 and 0.1 there. And so it's going to increase because there's a bigger difference between the two. If you use a smaller sample size, so that's going to make it decrease. A smaller sample size gives less information about the true proportion P. Bigger sample size makes it smaller, bigger, I mean. Okay, done with the lesson. Let's just try a few example problems here. So Amazon is one of the largest internet-based retailers in the world. The company offers a Prime membership for a fee. You probably know that. Report states that 46% of U.S. households, wow, have Prime memberships. Penelope wants to know if this proportion is different from her large hometown. She selects a random sample of 80 households. Notice she said different, not greater or less. It finds that 43 of them have an Amazon Prime membership. Is there convincing evidence? So, the first thing you might just look at, is that the same or not? What's 43 divided by 80? In this case, 53%, which is more. But again, it doesn't really matter as long as it's not the same. So we have some evidence to continue checking this. So you want to check the different things. So we want to, what's the null and alternate? So it's going to be, not equal to. It's a two-sided test in this case. Alpha level is 5%. Check all the conditions, right? So make sure you do NP. So 0.46 was P, so you're going to multiply that. And we check the conditions. Figure out all the stuff there, so plug into the formulas. The toughest part there, if you caught it, is when you do norm CDF here. So you got a z-value of 1.39. So then you go menu, 652, and I guess it'd be 1.39 is our z-value all the way to infinity. I'm just going to type a big number there. And you can, because it's z, we can leave those. You get that number, but that's not the answer. You have to multiply that by 2 because it's a two-sided test, so it should be 0.1646. So that's the tough step to remember here, is you've got to multiply it by 2. However, if you did this whole thing in the calculator, it'll do it for you, and you won't make a mistake. So it'll catch your mistake, in other words. So if you do one prop z test number 5 there, it's 0.46, 43 out of 80, I believe, and not equal to is there, and so it should give you that same 0.164. If you do this, you have to write down the z, the p-value, and the p-hat, probably the n. You might as well write them all down, but those three for sure, if you do it. And again, that'll catch your error. So if you do it by hand and then double check yourself in the calculator, you will catch that mistake for sure. Conclude, because our p-value, 16% is bigger than 5%, we fail to reject the null. We do not have evidence. We do not have evidence that the proportion of households will have an Amazon Prime member differs from 46%. So we don't have enough evidence to say that's true. The CDC and prevention claims that 11% of American children ages 4 through 17 have ADHD. company claims it has developed a new vitamin tablet that will lower the risk for ADHD. Researchers will administer the vitamin to 200 children volunteers at the age of 4. The subjects will be tracked through childhood, and researchers will record the proportion of subjects who develop ADHD. They're going to test at the 5% significance level. The null is nothing unusual. 11% have ADHD. The alternate is we think this medicine might be working, and it's going to be less than 11% that have ADHD. Where P is the true proportion of all children in the study who would develop ADHD when given the new tablet. The new vitamin tablet is expensive to produce, so researchers would like to be convinced that it really does reduce the risk of ADHD. This is the kicker. The power of the test to detect that P equals 0.05 is 0.937. Interpret this value in context. So let's remember what power is. So power is the top right square there. It's when you reject the null correctly, and the alternate really is true. The null is not true. The alternate is true. So you come to the correct conclusion, you reject the null. So the power of the test is 0.937. So given that the proportion of folks with ADHD is, the true proportion is P equals 0.05. That's what they said. There's a 93.7% chance that the alternate is true. I believe that's it. Let's see what they said. So if the true proportion of all children in the study who develop ADHD when given the tablet is P equals 0.05, there's a 93.7% chance or probability that the company will find convincing evidence that the alternate is in fact true, or less than 11%. So that's the interpreting the power. It's kind of tough to do. You got to kind of, if the stat they're saying is true, then that's the probability that they will correctly reject the null and accept the alternative. In the preceding skill, they want to test out that. Okay, so earlier we mentioned the power of the test, that is 0.937. Determine whether each of the following changes would increase or decrease the power of the test. Explain your answers. Okay, so if alpha went down, so alpha went 0.1 instead of, no, went up. Alpha 0.1 instead of 0. So alpha went up. So that means that beta, I don't know, beta is going to go down, right? This is type 1. This is type 2. So those work opposite of each other. So if alpha is 0.1 instead of 0.05, alpha went up, which means beta goes down. Type 2 error is going to go down. Type 1 error is going up. If type 2 errors, these two work, the power works exactly the opposite. So if beta goes down, power is going to go up. Type 2 and power are complements of each other. One's 10%, the other one's 90%. One's 80%, the other one's 20%. So they definitely go. So I think the power should increase here. Let's see what they say. Increase using a larger significance level makes it easier to reject the null when the alternate is true. Okay, let's look at the second one. So number 2, or part B, if the true proportion is P equals 0.08 instead of 0.05. So 0.08. So let's look at, there's the alternate. So let's look at that. So the null is P equals 0.11. If the true proportion is P equals 0.08 instead of 0.05, so 0.08. Okay, so the P value, the P is 0.08 instead of 0.01. So the null is 0.11, right? That's the null here. And 0.08 is less of a difference. So the power is going to go down, right? Because the bigger the difference, the greater the power. So if you get a sample where you get something a lot different, like it's gonna give more power. So it's going to decrease. It's harder to detect a smaller difference between the null and alternative. And finally, if the sample size is 500 instead of 200, that's going to be better. A larger sample size gives us more information about the true proportion P. So it's going to increase the power of the test. That's the lesson for today.